So today's lab is about current and resistance. So first off, what is current? So current is, if I had, say, a wire, so here's my wire, and then we're going to apply a potential difference across the wire. So here is my potential difference. So this is going to be represented by a battery. So delta B. So in a battery, usually we draw that with a long bar with a short bar, where the short bar is the negative side, and then the long bar is the positive side. So that's this guy. So basically what that ends up doing is that creates a potential difference across this circuit element here, or this wire, and then that creates an electric field. So in this case, our electric field is going to point this way. So it's going to be our direction of our electric field. So let's pretend that we don't know that charge carriers are actually negative charges, that they're actually, say, positive charges. So here we're going to take Q then is greater than 0. And then what we're going to do is, by this electric field being across this wire, that then creates a force onto our charge carriers in the same direction as the electric field. So this is our electric force. So what current is then is current is the motion of the particles then across this wire. Now, since this thing is feeling a electric field, meaning has an electric force, these guys should be accelerating on average, but it turns out that, as we'll talk when it comes to resistance, these guys end up making a lot of collisions, mostly elastic collisions, which causes them to actually move slowly across the wire, which means that these things, instead of accelerating across the wire, they actually feel an average velocity, which is what's called the drift velocity. So what you can think of then as current is basically the drift velocity. So what's the average velocity at which these guys move through? So how do we then define current? So what current is we're going to take this wire, we're going to chop it into a cross-sectional area. So here I'm just going to chop out a cross-sectional area of area A, and then simply we're going to count the number of charged particles which pass through this area. So if I have one charged particle moving here, another one coming through here, another one coming through here, another one coming through here. So in this case, what we call the current, we denote that by I, is then equal to the number of charges divided by the change in time. So this then is equal to, again, the number of charge carriers which basically pass through this, divided by the change in time, where the change in time is then just some interval of time that we're looking at. So this thing then has units of coulombs, because that's a unit of charge, divided by the unit of time, which is seconds, which is a coulomb per second, which gets a fancy name, which is called an A, which is equal to an ampere. So ampere then, represents the current, which again we can think of as basically the average velocity. So you can think of then current as then being directly proportional to this drift velocity here, which is also known again as the average velocity. Now, one thing that is different about current and average velocity or drift velocity is, remember, velocity is a vector, which means it does depend on direction, where current actually turns out to be a scalar quantity because charge and time are both scalars. So they're not directly the same thing, but they are directly proportional to each other. We'll talk about how that is in class. So this quantity here is, again, what's actually called the average current. If we want the instantaneous current, then the instantaneous current then is equal to the limit of this average current. So actually we'll put a bar on top of here for the average current, and the time delta t goes to 0 of then our average current, which is then equal to the limit as delta t goes to 0, pardon me, of then the change in charge divided by the change in time, which is then equal to the derivative of the charge with respect to time. So this is if I had a non-constant current and it's constantly changing, then this tells me that the instantaneous current, just like the instantaneous velocity, is then the rate of change of the position with respect to time when it comes to velocity, or in this case, the rate of change of the charge with respect to time, if I could actually speak. So good. So this is what we call current. So again, current is, as these charged particles are trying to move through this wire, or any circuit element for that matter, they're trying to then be accelerated by this electric field, but they can't really be accelerated because there's other stuff in the way. So basically these guys are making constant collisions all the time. So they end up moving across this wire or circuit elements with an average type velocity, again, what's called the drift velocity. So again, we can think of the current then as being kind of the average velocity. So why do these things constantly make collisions, and why do they kind of move slowly across this wire? Well, this has to do with what's called resistance. So if I look at the wire itself, so let me kind of blow up the wire here. So here's a bigger picture of the wire. So the wire is made out of a metal, which basically means that there are atoms everywhere on the inside of this, so metal atoms. Right? So here are my metal atoms. So good. So here, again, let's say our electric field points in this direction. And again, I'm going to take a charged particle. Whoops. Put that charged particle here, charged particle Q, and I want this guy to accelerate across. So again, this guy's going to feel a force. That force is going to be in this direction. So again, this is the electric force, which means that the acceleration will be in the same direction as the force. Right? So this is the direction of my acceleration. Now, again, what this particle is going to want to do is it's going to want to accelerate. So it's going to accelerate for a little bit, but then it's going to make a head-on collision with this atom here. Let me try a different color. Use black instead. So this guy's going to accelerate. It's going to make a head-on elastic collision with this atom. It's going to bounce off, come back, maybe another collision, because again, it's always feeling acceleration in this direction. And it's going to bounce off of him, and then maybe hit this atom, and then bounce off at this one, 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 etc. So this thing is constantly changing directions, constantly bouncing backwards, causing it to always have to increase speed and decrease speed, which means if I look at it at a moment of time, this thing is constantly having a different actual instantaneous velocity. But if I average the distance of a wire, so let's say this is a distance of a wire versus the time, delta t, then it takes a certain amount of time for this guy to cross the wire. And again, this is what we call the average velocity, or the drift velocity. So this is resistance. So resistance then is that any circuit element, including a wire, is built up of atoms. So I'm trying to constantly accelerate this electron, this charged particle across this circuit element or across this wire, but it's constantly making these elastic collisions, causing it to speed up and slow down, which eventually takes it a long time to make it across here. So this is what we call resistance. So it turns out that if I plotted the potential that I put across this wire, so again, let's put a potential across here, versus the current that I measure across here, this ends up being a straight line where the slope of this line is exactly equal to the resistance. So this is what we call Ohm's law. So Ohm's law says is that the potential that we supply across the circuit element, whether this is a wire or something else, is then equal to the resistance times then the current. So this is what we call Ohm's law. Now, one thing to pay attention with Ohm's law is this thing only works for metals. It doesn't work for anything else. So things like diodes and superconductors and semiconductors and all that different stuff. So all of that has a different relationship between the potential and the current. So this is more like Ohm's good idea for metals as opposed to Ohm's law, but whatever, that's fine. We're not going to nitpick too much. So anyways, this is resistance. So again, resistance is the fact that this thing is constantly making collisions and constantly causing it to speed up and slow down. Now, this is also the source of the fact that wire heats up, because as the charged particle here makes an elastic collision then with the atoms then start to vibrate faster and faster and faster, because they're embarking more and more amounts of kinetic energy onto them. And as the kinetic energy goes up, the temperature goes up as well. As you remember from this is the change in kinetic energy is equal to 3/2 kB times T, right? Or in this case, delta T. So the change in kinetic energy then is equal to 3/2 kB times delta T, which is what's known as kinetic theory, which means as the kinetic energy changes, goes up, the temperature also goes up, and then this temperature, or the increase in temperature, then gets radiated off as heat. So this thing ends up heating up and gives off a lot of energy due to the fact that this thing is actually heating up. Due to the fact, again, I'm trying to accelerate this guy across here. So how do I understand then resistance? Well, resistance is, let's go back to this picture. So here we can say then is what? If we think about a resistance then as the probability that the charged particle is going to make it across this wire, then we can say that's what? Resistance then is basically equal to the probability that it won't make it. So what factors give us a higher probability then? Well, we have the length of the object, right? We also have the cross-sectional area, and then we have basically the density of the atoms, which in electricity, we don't really call it density, we call this thing resistivity. So, but again, resistivity we can kind of think of as density. So good. So let's talk about resistivity first, or density. So would the probability go up that it doesn't make it, or go down if I increase the density? Well, if I increase the density, I'm going to have a lot more collisions, and as more and more collisions occur, then the probability that the charged particle is going to make it through is going to go down, which means that's what? The probability that it won't make it is inversely proportional to that, which means that the probability it won't make it is then going to increase as the density increases. What about the length? Well, if I increase the length, meaning I have to go a lot further to get across this thing, well, then we'd also expect then that the probability that it won't make it also is going to increase. And what about the cross-sectional area? Well, the cross-sectional area here is if I make the cross-sectional area smaller, again, now I'm going to tightly more pack these atoms into each other, which means that it's going to be harder for this charged particle to make it through. So again, this has to be now proportional to 1 over the area. So this is what we call resistance. So resistance then is equal to the resistivity times the length divided by the cross-sectional area. So resistance has units of, so according to Ohm's law, this is a volt per amp, and a volt per amp is what we call an ohm. So it's a capital omega, so this is what's called an ohm. And then resistivity here, so based off of this is what? Ohms on this side. This side has to be ohms as well, but this is resistivity times meters divided by meters squared, which is the same thing as resistivity divided by a meter. So it means this has to have ohm meters worth of units. So this is my resistivity. Right. So in this lab, basically, we're just going to be playing with this. So what you're going to have is a nichrome wire, where that wire you will not cut. Okay, it says that in the lab manual. Remember, we won't cut that. So basically what you're going to do is you're going to make some simple circuits, and they're all going to involve this nichrome wire. Now, there's going to be different types of nichrome wire. So we're going to play with the length of it. So in one part, you're going to have the full length, and then versus the half length, you're also going to play with the cross-sectional area. So you're going to have the same length, but different cross-sectional areas. So you have a thin wire and then a thick wire. And then also we'll play with the amount of potential that we're supplying across it. But since they're all nichrome, that means that the resistivity is exactly the same. Okay? So basically the quantities we're going to be playing with are the length of it, the cross-sectional area, as well as the amount of potential that we put across it, to play with then Ohm's law. Okay? So again, Ohm's law simply says that the current is directly proportional to the amount of potential that we put across. So that's basically it. So the first part is just kind of using now the ohm meter, so, or the ammeter, I should say. So what's an ammeter? So an ammeter is also going to be with the multimeter. So if this is my multimeter, so here's my screen. Here is my knob. And then down here, again, we have those 3 holes. Right? So the one hole was a COM. I believe that was the right-hand one. The center one then was the potential as well as the resistance, and then the left-hand one is what's called the ammeter. Right? So here, instead of putting your wires into these two, I still need a wire always in COM. So I'm going to have a wire coming out from this side, which is going to make it an ammeter, and then coming out through the COM. Right? And then this is going to be hooked up to our circuit. Now, one major difference between a voltmeter and an ammeter is, even though you're using the same piece of equipment, it's hooked up differently. Which basically means that when you're using an ammeter versus a voltmeter, you have to use an ammeter in series with everything else, as opposed to a voltmeter, which you use in parallel. Which basically means that, what, if I was looking at a simple circuit, so here's my battery connected then to a resistor, back to the battery, so just gonna make as simple circuit as possible. If I want to measure the potential difference, what I would do in that case then is I would connect my voltmeter in parallel across this guy. So basically I'm going to put one probe before the resistor, one probe after the resistor, and this is what's called in parallel. It's called in parallel because the current which is coming through here, by the time it gets to this point, which is what's known as a junction point, or a node, has the ability to split off, which basically means if this has current I running through it, some of the current then is going to go down through this centerpiece. So this is going to be another current. Let's call that then, I don't know, I1. And then some of the current then is going to go through the ammeter in this direction, or sorry, voltmeter in this case, current amount of I2. Okay, so this is our voltmeter. Now, there's something special about the resistance of then the voltmeter to basically make sure little to no current is actually going through the voltmeter. So the amount of current I1 is pretty close to that of I, and the amount of I2 is going to be approximately equal to 0. Okay? So basically in an idealized situation, this guy is going to be approximately 0, and this guy will be approximately then equal to the current I. Okay? Now, when it comes to the ammeter though, so if I draw that same simple circuit, so when it comes to this guy, what's going to be different now is actually when I have currents running through my circuit. So again, if I have current running through here, so this is my current I, with the ammeter, what we do with the ammeter instead is we put it in series, which means that basically we're going to break this line here, and then we're going to insert our ammeter. So I'm going to cut out this section. So basically what I'm going to do is I'm going to reroute the wire then into the ammeter. So now the wire goes in here to the ammeter. This wire is not going to come back through to then complete the circuit. So basically the current then is going to go directly through the ammeter to then measure exactly what this current is. Okay. So how we're usually going to draw that schematically is I'm simply going to put this guy here, put in my ammeter, and then this guy's going to go directly through here. Okay. So again, positive side and negative side. So this is one major distinction between a voltmeter and an ammeter. So again, the voltmeter has to be connected in parallel, which will be important when you're actually measuring then the potential across the resistor, versus that with the ammeter, which has to be connected directly in line with it. So again, when you're using the ammeter, in this case, you're going to break your circuit, you're going to connect the wire then directly into the ammeter and then run a second wire out of the ammeter to make sure that I have current flowing. Because if I cut this at any stage, there's no current running through because it doesn't make a complete circuit. As opposed to, again, when it comes to the voltmeter, here you're going to just take two wires, connect those directly in front of and on back of then the resistor. So you're going to measure it across the resistor just like you did in lab last week when you're measuring the resistance across the light bulbs to then make a measurement of the potential, right? The potential difference across this guy. So again, this is all we're doing in this lab. So we're making 4 different circuits, and then we're just looking at the relationship between all these different 4 circuits. Right? And you're going to be making predictions about the current based off of Ohm's law and what you understand now about resistance and resistivity. So that's it. This lab should be nice and easy. Another quick one like it was last week.